Okay, welcome to the last demo theatre presentations of the day. So to kick us off, we've got Greg Chadwick from lowRISC.
Great. Well, thank you for the intro. So yeah, my name is Greg Chadwick. I'm the digital design lead at lowRISC, and today I'm going to tell you a bit about our Sonata project, which is funded by the UK government via UKRI and the Digital Security by Design program. So before I can tell you about Sonata, I need to tell you about CHERIoT. So what CHERIoT is it's effectively a RISC-V extension that has been developed by Microsoft, and it is based on the CHERI work that many of you may well have heard of, and it is backed by over a decade of academic research that was started off by Cambridge University and SRI International, and many others have worked on it since. And the core thing CHERI and CHERIoT gives you are things called capabilities. And these are used to provide strong memory safety to basically help alleviate something about 70% of the bugs that we see that are memory safety bugs that lead to security issues. And this is kind of the answer to that. Or an answer, I should maybe say. And with a capability, in the case of CHERIoT, you take your 32-bit address, your 32-bit pointer, and you expand it to a 64-bit fat pointer. And all memory accesses and instruction fetches need to go through a capability rather than a raw pointer. And the capability itself contains metadata. And this metadata gives you bounds on the addresses you're allowed to access with the capability, as well as the permissions you're allowed, what you're allowed to do with that capability. And that's what that top 32 bits is for. Crucially, capabilities are unforgeable. Software can't just create arbitrary capabilities. It can only derive capabilities from other capabilities, and that's all controlled by the CPU. So the CPU ensures that software can't just create a new capability. And capabilities are monotonic, so you can only shrink your permissions and your bounds, and this is quite a crucial part of the security model. The CPU starts with effectively 1, well, in the case of CHERIoT, it's actually 3, but let's just say 1 to keep it simple. 1 capability that allows you to do everything, and then you're going to partition that down and shrink it down and hand it out to different parts of the system. And then they can't expand back out again. And this allows you to isolate different parts of your software to provide these strong security guarantees. And CHERIoT has been developed for kind of like low-end compute, so your kind of embedded, your IoT, your operational technology use cases. And a lot of the prior CHERI work has focused on maybe higher-end compute, so where you're running on application class cores, you're running a full Linux OS, or indeed in the case of CHERI, there's an awful lot of work that has been done on BSD. And Microsoft built their reference CHERIoT implementation on top of our open source IBEX RISC-V core. And we've recently announced a collaboration with Microsoft to undertake DV on this, so we can take the CHERIoT IBEX core to kind of production grade IP. And so what the Sonata system is it's an evaluation platform for CHERIoT IBEX. It's to allow people to use CHERIoT IBEX and try it out in these use cases, in these embedded, these IoT operational technology use cases. So what it provides is a microcontroller-like platform. I say microcontroller-like because this fundamentally is an FPGA platform. This, by the way, is the board running some software right now, and there is an FPGA in the middle of this. It's very expandable. There's a whole bunch of different headers on there, and you've got Ethernet, RS-232, 485 serial, and various other things, so you can use it in a lot of different application areas. And we've designed it to be as easy to use as possible. So you've got all of your firmware load, all of your debug, access to virtual UART, power, and what have you over your single USB-C. And the programming method is this kind of drag-drop programming flow you may have encountered with things like ARM Mbed or the Raspberry Pi RP2040. It appears as a virtual USB drive on your computer. You build a firmware file, you copy it onto the drive, and away you go. And as with everything lowRISC does, it is open source. So all of the RTL, all of the software, and the PCB schematics and the layout is all licensed under Apache 2.0. So one question I'm just going to answer here is, why is lowRISC undertaking this work? Because, Microsoft did build this initial CHERIoT platform. Well, this isn't our first rodeo. As you may have heard in the keynote from our CEO, Gavin Ferris, this morning, we steward the OpenTitan project, and that has succeeded in producing commercial-grade open silicon. Earl Grey, which is going to be shipping in a volume slot, as recently announced by Nuvoton, is going to be utilized in Google Chromebooks. So we really understand what it takes to move from a nice piece of open source IP to something that can actually become a production grade product. And that is what we've done right here. So this is the OpenTitan Voyager board. That is an OpenTitan chip in the center there, and that is actually running an IBEX core. Not a CHERIoT IBEX core, that's the vanilla IBEX. And so with Sonata, PCB here, we're not taking it to the same level as OpenTitan. We're not, with the currently funded project, we're not producing silicon, but we know what you need to get there, so we're pushing it as far along as possible in this FPGA platform to help it on the path to productization and commercialization. And we're already shipping out these boards, so this is just the Sonata board packaging. We've already shipped out 103 boards that have been funded by our grant from UKRI. And there's going to be a commercial version available shortly from Mauser. I think we're targeting kind of early July. And if you want to, you can just build your own because the schematic and layout are available. It's currently in Altium format, and work is ongoing on a version for KiCad because that's a lovely open source bit of software, and we want to support it. So that is everything for the talk. I am now going to show you something about how you actually use Sonata. So as I said, you have this kind of drag-drop programming flow. So right now, this is running this program, and I have a little Hello World demo here. I'm going to copy this file. I'm going to put it on the Sonata drive. And then I'm going to jump in here, and we're going to open up the serial terminal, and it's now running our lovely Hello World program. Very quick and easy. And just as a little demonstration of what the software build looks like, let's modify this program. So we're going to say hello RISC-V Summit. Oh, that was not the thing I wanted to do, but never mind. Jump over here. Do I mean jump over here? This was all set up nicely, and then I've messed something up. Sorry. Let's do this. Sonata software. So we use a thing called NIX to help set up the development environment. I'm not going to go into NIX, but basically you run that command, and boom, you've got a shell that has everything you need to build Sonata software. I run the build command. I then do a copy. Yep. And we're going to copy what we've just built onto that Sonata drive. Wait for that to finish. Reboot, and here we go. I've just got the lovely new program up and running. Very quick and easy, straightforward. If you want to, you can delve into the RTL. You can build your own FPGA image. You can do all kinds of things. If that doesn't interest you, then, well, ignore that, and you've just got our nice, easy build system, or I should say the CHERIoT RTOS build system, and it just allows you to quickly get up and running and use this like you might use any other embedded development board. Now, the next demo I have for you is a more interesting demo, and it's around the CHERIoT security model and compartmentalization. So what I have in here is a JavaScript interpreter, which I'm loading onto the Sonata board now. There we go. And this was all set up nicely, and apparently I've removed a useful terminal somewhere. No, this is what I need. And now I'm going to load just a Hello World JavaScript program on this. So this is pre-compiled JavaScript running to code, and you can see it running on the board now. And it's flashing some LEDs, and it's saying Hello World. Excellent. At the top here, if it wants to stop, which it will do, there we go, it tells you we have a secret stored at this particular address. And if we jump over here, we have this C file included in the build here. And it has a secret value, and it is a C static variable, so it is only accessible from C code within this file. And within this file, it doesn't allow you to get the secret out, you can just check the secret. So fantastic, our secret is isolated within the C file, no one can get at it, right? Well, I think anyone who's written C knows that's absolute rubbish. We know the address of that secret variable, we can read that address, we can get that secret. And unfortunately, our JavaScript interpreter is massively compromised, and an attacker can read and write arbitrary memory via JavaScript bytecode. And that's what we're going to do right now. So we have this leak. That is going to load onto the board, and there we go. Oh dear, we've leaked the secret. Because the JavaScript interpreter is compromised, the attacker cannot access arbitrary memory. It doesn't really matter that we've got a bit of kind of soft, abstraction within the C code to attempt to isolate the secret. It's totally useless. So that brings us on to CHERIoT compartmentalization. So here, we rebuild the software, but we do it a bit differently. Now this piece of code, this secret, This lives in its own compartment, in a different compartment from the JavaScript interpreter. I'll load that onto the board. And then we will, oh, wrong command. We're now going to try and run the attack again. And it doesn't succeed. The JavaScript compartment crashes. It attempts to access the memory address, but it physically cannot. The CPU will not let it because of the CHERIoT capability checking, and it just can't get at that secret. So we have a totally compromised JavaScript interpreter, completely broken. Attacker can do whatever they like, as if they could write the C code in that compartment, and it doesn't matter. Our secret is nicely isolated with its well-defined interface in another compartment. And that is the kind of fundamental building block of CHERIoT RTOS that allows you to provide very strong security that you don't normally see in embedded applications. And crucially, that JavaScript interpreter, we didn't have to rewrite that. That's the Microvium JavaScript interpreter, same piece of C. We wrap it in a compartment, that's it. And suddenly, you've got rid of a whole class of different attacks you might otherwise have not been able to avoid. And there we go.